Welcome back once again, Transistor lecture series. So in this lecture, we shall be solving one more numerical on self-bias method. Now the problem statement is draw the DC load line and determine the operating point. Assume this is a silicon transistor. Further, find the stability factor if beta is equal to 50. Use Thevenin's equivalent circuit. So let us see the circuit. So it's a self-bias circuit, and if you look into it, this is same as the previous problem that we have solved, but here the method will be different because here we are asked to use the Thevenin's equivalent circuit. So what all are given here? All the resistor values are given. Transistor type is said a silicon transistor, that means VBE is 0.7 that we shall consider. Beta is given as 50. Okay, so all these information are given to us. Now we have to reduce this network, voltage divider network, for Thevenin's equivalent circuit. Now Thevenin's equivalent circuit, we know that we shall have only one voltage source and one resistor. So this is how we have to reduce this circuit. So if we reduce this circuit, the voltage source that we are considering, that will be the drop across this R2. So let us consider that as E0, and the equivalent resistor for this network will be R0, and R0 is nothing but R1 parallel R2. So this will be the Thevenin equivalent circuit of this entire section. So we can now redraw this circuit as we have the transistor and we have the emitter resistor. So now this is plus VCC. Now in the input section, we have the equivalent resistor R0, and we have a voltage source which is responsible for biasing the base emitter junction. So here the voltage drop is VBE, this is E0, and this is RE. Okay, we have here RC also. So all these values are given here, same value we shall be taking. Now R0 is given as the R0 R1 parallel R2. So that is R1 into R2 divided by R1 plus R2. So all the resistors are given in kilo ohms. So R1 R2 value 10 kilo ohm and 5 kilo ohms. So we can write it as 5 into 10 50 divided by 5 plus 10 15. So that will give us the value 3.33 kilo ohms. So R0 value we have got as 3.33 kilo ohms. Fine. So now what is E0? E0 is the voltage drop across R2 resistor. So that will be given as VCC into R2 divided by R1 plus R2. So whatever we shall be getting, you can execute this VCC. Now here you can see that VCC is not given. So if it is not given, then we can consider any value. For this purpose, let us consider it as 15 volt. If it is not given, we are free to consider any value, 10, 15, 12, whatever value we want we can take. Generally 12 or 15 volt are considered. So here I have chosen 15 volt. Even in previous problem also I have chosen it as 15 volt, but you are free to choose any other value also. So now if we put this value 15 volt and R2 value is 10, R1 plus R2 is 15. Okay, no, R2 value is 5 kilo ohms. Okay, so R2 value is given as 5 kilo ohms. So 1/3 of 15, that is 5 volt. So E naught is, now we have 5 volt, and R naught we have as 3.33 kilo ohms. So this is 5 volt. Okay. So now let us first find the DC load line. So we know to find the DC load line, we need to analyze the output section of the given circuit. So output section will be as it is. So we can write VCC, that is equal to drop across RC. So IC into RC plus VCE, this drop, and drop across RE. So that is IE into RE. Now in our assumption of self bias, we have considered IE equal to IC, since IB is very small compared to IC. So we can rewrite this equation as VCC equal to VCE plus IC RC plus RE. So this is equation 1, or we can rearrange this with VCE, that is equal to VCC minus IC into RC plus RE. So this is our output equation. Now from this output equation, we can find the DC load line. First, we shall consider VCE equal to 0. So this will imply that IC value is equal to VCC by RC plus RE. So substitute the values of VCC, that is 15 volt, RC and RE value we have considered as 1 kilo ohm and 2 kilo ohm. So RC plus RE will give us 3 kilo ohms. So 3 into 10 to the power 3. So that will give us IC value as 5 milliampere. So we have got IC value 5 milliampere. So that is one end point of DC load line. Similarly, in equation 1, if we put IC equal to 0, that will give us the VCE value as VCC. So that is 15 volt. So now we can draw the DC load line, VCE in volts and IC in milliampere. So 2 points we have got, 2 endpoints. So we'll connect these 2 points and we'll get the DC load line. So this point is 5 milliampere. So that means this point is 0.5 and this is 15 volts. So we are getting this point as 15.0. So this is our DC load line. Next, we shall be finding the operating point. Now to find the operating point, we have to find we have to analyze the input section. So in the input section, we have, this is our input section. So this is our input section. So here we have E naught that we have found as 5 volt. This is R naught that we have found as 3.33 kilo ohms. Okay. So this is our input section. And here we shall apply the KVL. So emitter current we have considered as equivalent to the current of collector current, and emitter current equivalent that we have considered. So if we apply now KVL over here, we can write E naught, that is equal to, this is the current IB. So this is current IB we are considering. So E naught is drop across this resistor. So R naught into IB plus VBE. So this drop we are considering, and plus IE into RE. So as we have considered IE equivalent to IC, and also IC is equivalent to beta IB. So we can replace here IE as beta IB. So you can write it as E naught, that is equal to R naught IB plus VBE plus beta IB into RE. So you can take IB common. We are getting E naught, that is equal to IB into R naught plus beta RE plus VBE. So this is giving me the input equation. So from here we can find the value of IB. So IB is equal to E naught minus VBE divided by R naught plus beta RE. So now if we substitute the values, VBE, we have already seen that it's a silicon transistor. So we can consider this value as 0.7 volts, and E naught we have found as 5 volt, and R naught we have found as 3.33, and RE is given as uh, RE is given as 2 kilo ohms. Okay. So further, uh, the operating current we can find ICQ, that is equal to beta IB. So IB value we have found from here. So directly instead of evaluating this one, we can directly evaluate ICQ, or if you want, you can first evaluate this one, then find IB, and then put IB over here to find the ICQ. Both way it is possible. So anyways, we'll be now substituting the IB value here. So beta into E naught minus VBE divided by R naught plus beta RE. So here, if I divide this beta, if I divide this one by beta, beta I am taking down here. So then we can write it as E naught minus VBE divided by R naught by beta plus RE. Now see here, R naught by beta, R naught value is very small compared to beta. So we can say RE is much greater than R naught by beta. So in that case, we can ignore this value and we can write ICQ, that is equal to E naught minus VBE divided by RE. So now if you substitute all these values, you can get the answer as 2.15 milliampere. So this is the value of collector current for finding the operating point. Similarly, if we substitute this value ICQ in the output equation, in this equation if we substitute the value, then we can find the value of VCEQ. That value we'll find as 8.55 volt. Just substitute these values. Here I am not showing these values. Just put these values of ICQ here instead of IC, and RC RE already given, VCC we already know. So if we solve this equation 1, we can find VCEQ equal to 8.55 volt. So here we are getting some point where ICQ value is 2.15 milliampere and VCE value is 8.55 volt. So this is our Q point and the coordinate is 8.55, 2.15. So operating point we have found. So first we have found the DC load line, then we have found the operating point. Now for finding stability factor, it is given as 1 plus beta into 1 plus R naught by RE divided by 1 plus beta plus R naught by RE. So R naught value we have already found as 3.33 kilo ohms, and RE value is given as 2 kilo ohms. So substitute these values. S equal to 1 plus beta is given, beta value is given in the question as 50. So 1 plus 50 into 1 plus 3.33 divided by 2, both are in kilo ohms, so no need to write 10 to the power 3 here. So 1 plus 50 plus 3.33 divided by 2. Now if you solve this equation, you can pause the video and do the calculation. So we'll get S equal to, stability factor equals to 2.58. So you see that S value is very near to the ideal value. Ideal value of S we know is 1, and here this value is very close to the ideal value. So whatever transistor circuit we have designed, the self bias circuit we have designed, it is a very stable circuit that we can conclude. So same numericals we have solved in two different methods. Previous video one method we have followed, and in this video we have followed the Thevenin equivalent circuit method. So here we have reduced the self bias circuit with the Thevenin's equivalent circuit, and we have found this circuit. Further we found the DC load line on it and operating point on the DC load line, followed by the stability factor. So here we end this discussion. Thank you.